Good day, seniors. Today we're going to start a 2-week look at Feynman diagrams. Now, the point of this whole endeavor is not to become experts at particle interactions and what's going on a very, very small scale, but to simply appreciate some of the things going on a scale much smaller than we can possibly imagine. Okay, this is not stuff you're going to see freshman year of college, but I think it's very interesting. And so we're going to take some of these last few weeks and talk about some particle physics stuff and a few other little topics. This week, we're going to focus on conservation laws. You should have seen a video before this talking about Richard Feynman and some of the things he did. And certainly, we're going to be diving next week heavily into Feynman diagrams. This week, though, we're going to set this up. Let me basically set up a simple situation. Imagine you have an electron. These two electrons are moving towards each other. And you ask, what's going to happen as time moves on? Well, the two electrons should get closer and closer together, but they're opposite charges, and we know because of Coulomb's laws and all that they are going to be repelled from each other, and so they will fly apart from each other. And we can do this physics, okay? We can calculate how close they'll get to each other depending on how much energy they have. We can calculate the amount of potential energy they might have at closest approach, whatever. We can do that kind of math. But that's sort of looking at things on the macro level. What we want to focus on today is, well, why does that happen? Why are those two electrons ejected from each other, repelled from each other, and what's the physical phenomenon going on behind the scenes? And this is really where Richard Feynman stepped in. As we were discovering this quantum world, scientists could describe this interaction with some very, very complex mathematics. They could do some very complex algebra with all different kinds of variables and perfectly describe what happens here. But it was very, very difficult and well beyond the scope of what we're going to be doing at our level. In stepped a guy named Richard Feynman. Now, what Feynman did is he didn't invent new physics. What he did is he figured out a way of expressing how these interactions occurs that allows people to, even at the high school level, to easily write out how particles could interact with each other. And it turns out there are many ways this could happen. Okay? There's a lot of stuff that can happen when two electrons come together. Some are more likely than others, and we'll get into that with Feynman diagrams certainly. But we're gonna understand the basics of what's going on between these electrons. So that's sort of the end goal. We're going to be focused on this. We'll also focus on decay. We'll talk about beta decay. That's something we talked about with nuclear. And if you remember, beta is sort of weird because beta decay is the one that has the neutrinos. They have the neutrinos that are doing some weird things. And we're going to start looking at that and diving into that next week. This week, though, we're going to describe really, sort of what's going on here and why and how we know that. So before we start, I want to talk about conservation. Now, we've had many, many different laws of conservation before. Law of conservation of energy. The amount of energy you start with is equal to the amount of energy you end with. Now, you might say, Mr. Reynolds, that didn't work in a nuclear chapter. Our energy went up, mass went down. I'm sort of combining mass and energy because they really are the same thing there. Conservation momentum. When two things have collisions, the total momentum stays the same. And in fact, those two, energy and momentum, they certainly still exist with these particles. So if I look at the momentum of the first electron and I look at the momentum of the second electron, the total momentum between them before the collision is equal to the total momentum after the collision. That is totally still the case. If I look at the energy of anything coming into the situation and look at the energy of everything coming out of the situation, the energies are still totally the same. That has not changed at all. These two electrons are coming together. I would not expect them to both start moving down after the collision. That would break the law of conservation momentum. I wouldn't expect them both to fly off at a much higher velocity. That would break the law of conservation of energy. Okay, those things still exist, but those aren't the conservation laws we're going to focus on right now, because there are a couple other conservation laws, and these conservation laws govern what type of particle interactions are are available and even doable. So we have the law of conservation of charge. The total charge before the collision is equal to not only the total charge after the collision, but also the total charge at any other point within the collision. And we'll talk about how that works a little bit later on. We're going to be talking about baryon and lepton numbers. Those are always conserved. Okay, so the baryon number before the collision has to be equal to the baryon number at any point during this interaction. And also strangeness is conserved. Now, if you remember before spring break, we talked about strangeness as a property really of only the strange quark and the anti-strange quark. But strangeness is conserved with a little asterisk up here. And strangeness is not conserved in weak interaction. And we'll talk about what that means in just a second. Okay. So other than that, these laws always have to be conserved. At any point in the collision, all 6 of these things need to be conserved at all points. Now, if you go up, if you remember back to our Feynman diagrams, you should have created your own Feynman diagram. That was one of the assignments for one of the previous weeks here, is we have our standard model. These are the elementary particles, the particles that, as we know of now, cannot be broken down into any smaller pieces. These are as fundamental and basic as they get. We have the quarks, we have the leptons, we have the bosons. Okay, if you remember, by all these together are fermions, and these are bosons. The quarks, up, down, charm, strange, top, bottom. Remember the light ones, up and down, those are by the far most common. You'll run into these other ones, very unlikely. Leptons, same thing, the very light ones are most common. The other ones, less common. They all have charges. They have strangeness. Well, really only one of them has any kind of strangeness. They have baryon numbers, and they have lepton numbers, and all of these need to be kept in mind. The standard model that you made, you need to have out. If you don't have it, it's in section 7.3 in the data booklet, where it talks about all the numbers that you'll need to know. Now, it turns out that any interaction, I'm going to use the word interaction a lot. An interaction is when any one particle does something with another particle. Okay? When, example, 2 electrons run into each other. That is an interaction. When a neutron breaks up and turns into a proton and gives off some other stuff. That is an interaction. Anytime there's an interaction between some of these particles, you're going to have something being sort of the referee. You need something that's going to allow the interaction to occur. And these things are the bosons. So, for example, when our 2 electrons, when they are bouncing away from each other, one of these bosons is the thing that basically sends a message from one electron to the other saying, hey, we got a second electron coming in here, you might want to be turning around. It's going to be spreading that information, the energy, and so forth. All these carry energy, and these are all dealt with different types of interactions. So, for example, we have the gluon. Now, the gluon is the boson for the strong nuclear force. Actually, I've already got it written down there, so I'll just highlight that. The strong nuclear force, choose a different color. This is only dealing with quarks. So with our electrons that are bouncing away from each other, no quarks really involved there. They're electrons or leptons, so no quarks need apply. So the gluon is not doing the thing there. The gluon is the thing that connects the up, the down, and the proton, for example. A photon is any electrical thing. So any things with charge, in other words, these particles right here, those particles are all dealing with the photons. In this case, we do have a photon. This is a photon interaction between the two. The other type of boson is the three types. You have the Z boson, the W plus, and the W minus. These are all for the weak nuclear force. Now, these bosons deal with everybody, but most in particular, if you ever see a neutrino, you know that you are going to be dealing with one of these bosons down here, the Z, the W plus, and the W minus. Now, there are three of them, and you'll notice the charges really are the differentiating thing here. The Z has no charge, the W plus has a positive 1, W minus has a minus 1 charge. That's going to be very important because remember, at any point in interaction, the charge is conserved. There are no neutrinos dealing with here, and so we're really not going to deal with that weak interaction. This is a garden variety photon interaction. The photon is the thing going from one thing to the other. And so we can look at a basic Feynman diagram like this. I'm not going to spend a lot of time on Feynman diagrams today. We are going to look at some conservation laws and see, do these things work or not. But basically what happens in a Feynman diagram is we are going to draw two axes. Now these two axes, depending on the diagram, they're going to be listed different ways. Okay, so there are always two axes. One of them is a position axis. There's really no up or down to that. And the other is a time axis. Now, what we will usually be using is we'll usually be using the x-axis as time. That means as things move to the right, they're not moving to the right in physical space. They're just moving through time. You will also see time being upwards in a Feynman diagram. Okay, it just sort of depends. And so, for example, for this, these electrons, when they run into each other, we're going to have one electron starting up here, one electron starting up here. We're going to give them paths that look like this. We have arrows. These are regular particles, so we give them arrows moving forward in time. We'll talk about that more a little bit later. Now, if you look at this picture, you'd think that the two electrons are approaching each other at an angle. That is not the case. The electrons are simply moving closer to each other. This x-axis is not a position vector. It is a time vector. In fact, I'm going to back up a little bit here. Now, instead of these two running into each other, which is, we know, not what happens, the electron is going to give off a photon. Now, any boson, we're going to illustrate like this wavy line. No, I don't want you to make a shape. Thank you, Notability. Let me try that again. I'm not going to be so slow this time. There we go. It's going to give off a photon. That photon is going to be moving forward in time, and it is, actually, let me just try it. It looks a little too wonky here. Here we go. There we go. Nice little photon. That photon is moving forward in time. It is moving from the top electron to the bottom. Now, after that first electron gives off the photon, the electron now jumps up. The photon has some momentum. We learned that last chapter. And so the law of conservation momentum occurs here. And then when the momentum hits that, the other photon hits the other electron will rebound as well. And in this interaction, this is describing an interaction of two electrons coming closer to each other and then bouncing away from each other. Right? That's all this is showing. And the nice thing is, at any time, all of these things are being conserved. Momentum is being conserved at any point. Remember, the photon does have momentum, and so that's why you see this one having a different momentum. That's okay, because the photon takes up the rest. The energy is completely conserved. The charge. Let's take a look at charge here. Again, we're going into a lot more detail of this next week, but I'm just giving you a little preview. So at this point, at this time, we have only two electrons. The charge of the two electrons, this top electron's a -1, the bottom electron's a -1, and so the total charge is a -2. At any other time in this interaction, the total charge must be a -2. No other exceptions. Okay, so if I pick out here, Well, we have 2 electrons. Each of them's a minus 1. Minus 1, minus 1, minus 1, minus 1. And so we have a minus 2 charge. Okay, that works. Let's check right here at this time, right in the middle of that interaction. Well, we have 1 electron, we have another electron, and I know that boson, because the total charge must be minus 2, I know that boson must have 0 charge. We've already talked about what kind of boson that probably is. It's a photon, and if I go up, I can see that a photon indeed has no charge. Hey, that's pretty cool. So the charge is conserved. Baryon number, well, that's pretty easy. There's no baryon numbers with any of these because there's no baryons. So no baryon numbers, they're conserved, no problem. Lepton number, well, let's see. What's the lepton number of an electron? Lepton number of electron is a 1. So at this first time, our lepton number is a 2. At the end, our lepton number is a 2. And even in the middle, the lepton number is a 2. This thing's a boson. Bosons don't have lepton numbers. Finally, the strangeness. None of these things have any strangeness. And so, no problem. Strangeness is totally conserved. Okay, so this is an example of the law of conservations. This would be a valid Feynman diagram. And again, we're going to go into more details. Now, could you draw some other Feynman diagrams? You sure could. The video I'm going to show you after this will show you some variations on this Feynman diagram. Those variations do follow all the rules of the Feynman diagram, which we're going to talk about again a little bit more next week. And so they definitely could happen. However, the more things you may build onto this Feynman diagram, while they could happen, they become less and less likely. And we're not going to go into the math of how likely that might be, but they definitely can happen. So the conservation laws are very important. Let me give you one example of a problem you might see, I would say, on the test, but not having a test, so, whatever. We can look at a example here of... let's see. Well, I'm going to put a neutron. Now, a neutron is a down, down, up. That neutron is going to give off a proton plus an electron plus an antineutrino. Now, a proton is up, up, down. Now, I want you to pause the video right now. Ignore energy and momentum for the moment. That doesn't really matter at this point. I want you to go through and I want you to check all 4 of these conservation laws. And I want you to tell me whether or not this thing has matches. Whether or not this thing is a valid thing that could happen or maybe a not valid thing. Okay, pause and let's find out. All right, let's go ahead and check. So let's check charge first. Charge of a neutron, well, I know that. The charge is 0. That means the total charge, by the way, if you want to check, the down is a minus 1/3. The down is a minus 1/3, and the up is 2/3. If you add those 3 charges together, well, that's going to equal 0. Okay. The proton, if the neutron is 0 charge, then this entire right side must have 0 charge. Let's see if that's the case. Well, let's see. The proton has a plus 1 charge. 2/3 plus 2/3 minus 1/3. That's 3/3, which is 1. The electron is a minus 1 charge. The antineutrino. Well, neutrinos don't have any charges. Okay, they're totally chargeless. So, yeah. I was looking. Sorry, let's go up here. Yeah, neutrinos here, no charge at all. So no problems there. Plus 1, minus 1. That means the whole right side of the equation has a charge of 0. So far, so good. Let's check here. What next thing? Baryon number. All right, baryon number. Okay, well, remember each quark has a baryon number of 1/3. So 1/3 plus 1/3 plus 1/3 has a baryon number of 1. The left side of this equation must have a baryon number of 1. Let's check the right side. 1/3, 1/3, 1/3. The proton is a baryon number of 1. Sounds good to me. That's mainly because neutrons and protons are baryons. The electron. Well, the electron's a lepton. It's not a quark, and so there's no baryon number there. The antineutrino is, again, not a quark. And so, yep, total baryon number is 1. Baryon number checks out. Lepton number. Lepton number. Well, let's see. Neutron is not a lepton, so it has 0 as a lepton number. Proton, not a lepton. No leptons in it. Remember, lepton number is only for the leptons. Leptons, if you recall, are the electrons, muons, taus, all, and the neutrinos, that kind of thing. Just to remember, everything has a lepton number of 1 except for the antiparticles, which have a lepton number of -1. All right, let's see. The electron has a lepton number of 1, as we just said, because it is a regular lepton. The antineutrino. Well, the antineutrino, it's anti, so it must have a -1 lepton number, which means the total lepton number is 0. That checks out. Finally, the strangeness. Well, this one's sort of easy. Because, there's nothing strange in here. There's no strange quarks, no anti-strange quarks. 0, 0, 0, 0, stress 0. No problems. That does check out. And so this could happen. I'm not saying this is going to happen all the time. You might recognize this. This is beta minus decay. We're going to actually diagram this with a Feynman diagram next week. But it could happen. And so these conservation laws allow us to know whether these reactions can happen or not. And so this one can. Okay. So today we're focusing on conservation laws. Coming up next, I'm going to post a video where it's going to talk a little bit more about Feynman diagrams and sort of how they're used. I have a reading assignment on cognity about the Standard Model and conservation laws. So I want you to read that section, answer the questions inside the section, all that kind of stuff. And then I've provided there's a worksheet, a quick worksheet to sort of work out, and just some basic conservation laws. It shouldn't be too tough. But then finally, I am giving you it's a totally optional assignment. But if you're somebody that's into science, if you're somebody that's into, you look at this, especially nuclear stuff and quantum stuff, all these sort of weird things, if you look at this and say, man, this stuff's sort of neat, I'm going to put a link, I'll put it at the bottom of the Managed Back assignment, to a YouTube video where Richard Feynman is giving a talk to, I think, UC Santa Barbara or something like that, some school. And he's talking about... he's just talking about his experience with the Manhattan Project. He's talking about his experience making the atomic bomb, basically. He was one of the theoretical physicists there that designed it and did a lot of important work. And it's very interesting. It's like an hour, 10 minutes. So it's not a short thing. It's not an assignment. You don't have to do it. But it's something provided if you're somebody that, I don't know, maybe is isolated at home for some reason and you have... you're bored or whatever. If you're into science, this is worth a listen. It's a recording of him addressing a lecture and all this kind of stuff. I actually first was exposed to this in one of his books. He has a lot of very interesting books, and they've transcribed this in the book. But I would encourage you to take a look if you're interested. If you're not interested, don't listen. No problem, no harm, no foul, and not taking off points or anything like that. But give it a shot, take a listen, and hopefully you can, find something interesting in there. Next week, we're going to talk some more about Feynman diagrams. We're going to dive into a little more details, how to draw them properly, how to do all this kind of stuff. Again, I think this is some sort of neat stuff. This is active science. This is understanding things at a very basic level, which I think is going to be very important. So hopefully you keep with me here, tune in. I look forward to seeing you in our Zoom chat this week, and look forward to hearing what you think about all this. So, Mr. Reynolds, have a great day.